So much. So, hello everyone. Good day, good evening, depending on the time zone. I'm Federico Girella. I am a PhD student from the Interlegal Labs at the University of Verona in Italy. And I'm here to present our work titled Lots of Fashion, Multi-Conditioning for Image Generation via Sketch Text Pairing, which was awarded an oral presentation at SCCV 2025. This is a work in collaboration with the University of Verona, Fondazione Bruno Kessler, and the Polytechnic of Turin in Italy, and the University of Reykjavik in Iceland. So our work focuses on the fashion domain, and in particular on the creative process of outfit design. And in the initial phases of this process, designers make use of drawings or sketches of the items that compose these outfits to both guide the creative process and have an overall preview of what the final outfit might look like. In this case, for instance, we have an outfit composed of 3 items, which is a blazer jacket, a shirt, and some pants. Additionally, the designers also add textual notes that provide other attributes, textual attributes, that further describe the item properties. And as you can imagine, this process creates a lot of multimodal data, which can be also complementary in nature. For instance, when looking at the blazer, we can see that the sketch on the side, let me use the pen here, the sketch on the side provides clues about the presence of pockets on the side, which the description does not mention. And on the other side, on the other hand, when looking at the pants, we can see that the description provides clues regarding the presence of stripes in the final product, or their desire from the designer to have stripes in the final product, despite no stripes being present in the sketch. And again, this highlights the complementary nature of this multimodal data. In particular, there might be some properties that are easier to describe through text, such as stripes, patterns, and others that are easier to describe through sketches. So our goal, just to tease a little bit what the end of the entire process will be, is to develop a tool such as this, where a designer may draw the items that compose their outfits and pair them with their related descriptions. And once the entire outfit has been composed, we want to be able to generate an image of the final outfit as it would end up, with all the correct attributes localized. So this is our final goal. But before looking at how we do it, we wanted to give a bit of context on, some methodologies that already achieve something similar. And of course, there already are some methodologies that can generate images with sketch conditioning, and in particular, the popular T2I adapters or ControlNet, apologies, augment pre-trained text-to-image diffusion models with the ability to condition the image generation with an additional image, which in our case would be the sketch of the final outfit, or for the entire outfit, sorry. And these models work well. You can see the image looks very good. However, they suffer from a common issue, which is evident when looking closer at the image generated. So when looking here at the image, we can see that the model is wearing a striped blazer and a plain shirt. However, this is in contrast with the original input, which requested for a plain blazer and a floral shirt. In summary, these methodologies struggle to represent attributes, in this case, pattern attributes, in the correct locations, either leaking them to unrelated items, such as the stripes leaking from the pants to the blazer, or not representing them at all, such as the floral pattern not appearing in any item. And we refer to these problems as attribute confusion, which is a crucial issue in the outfit design process, as designers, when they're designing, they want the attributes to be correctly localized to give an idea of the outfit. So we aim to solve this issue with our project. And we start by investigating the possible reasons for attribute confusion. And there might be many reasons to attribute confusion, but we argue that it is mainly due to how these methodologies utilize the conditioning input. In the example we just saw, both the sketch and description were seen as global representation for conditioning, meaning that they were expected to condition the entire image by themselves, basically. And this creates a couple of issues. And in particular, we are providing only a single sketch and description, which relies on the model implicitly learning during training to identify which items appear in the sketch, localize them, and do the same for the description. They need to understand what part of the description relates to what item. And furthermore, there is no explicit link between the textual description and the sketch item, which again relies on the model to learn without any guidance to pair partial parts of the descriptions with the location in the sketch identified by the items. And this is a very complex task for a model without any guidance. So we argue that one solution might be to shift from these global representations to localized representations. And what we mean by localized representation is to create a localized sketch text pair for each item in the outfit. So for instance, we might have a sketch text pair for the blazer, one for the pants, and one for the shirt. And shifting to these localized representations, localized representations solves the issue previously presented, and in particular also allows the user to specify multiple localized sketch items, so the model doesn't need to learn implicitly to identify them anymore, and creates an explicit link between the partial text and the local sketch items. Furthermore, as we saw at the beginning, this type of paired data is available from the start of the design process, making data collection easier and the overall pipeline intuitive for the end user. So with this idea in mind, we present, with this idea in mind, we present LOTS, our localized text sketch adapter. And LOTS is an adapter module for text-to-image diffusion models, in our case, convolutional diffusion models, but it can be extended to others. So LOTS allows the user to use the localized conditioning that we just discussed, and also allows to compose the outfits with a flexible number of items, which is crucial as you may know, different outfits may be composed of variable number of items. You might have, for example, a single long dress for maybe a fancy evening, or you might have a more casual, jacket, t-shirt, pants combo for everyday life. And so we achieve this in a two-phase approach. We have a first pair-centric representation phase, pair-centric representation phase here, where our goal is to encode the information coming from the localized pairs that we just discussed. And the second diffusion pair guidance phase, where we want to inject this information inside the pre-trained frozen diffusion model for conditioning. So going to the first pair-centric representation phase, as I mentioned previously, we want to encode the localized sketch text pairs for conditioning. And the way we do this is by using pre-trained image and text encoders. And as you can see in the example here, each localized pair is fed through their respective encoders. So the sketches go through a Dino V2 image encoder, whereas the description go through a clip encoder. And the resulting features are then concatenated in what we call a paired feature set. In cases such as this one, where multiple items compose the outfit, we repeat the process independently for each pair. And this is done to avoid any information leakage between the pairs and is our first step towards reducing attribute confusion. So once this step is done, although the features have been encoded and paired, they still reside in vastly different feature spaces which in our experiments created some issue during training. And in particular, what we noticed is that due to the sparse nature of the sketches, where, as you can see here in this example, only some regions of the image contain trunk information, with the majority of the regions being empty, this resulted also the sketch features to be very sparse. And during training, this causes the model to ignore the sketch information altogether, instead only focusing on the textual information. So we want to solve this, and the way we do this is by introducing the pair former, which is an attention-based module for information fusion and compression. So in the pair former, the paired features are concatenated to a set of learnable tokens, and then this concatenated sequence goes through a self-attention pooling mechanism, which is basically a self-attention attending all tokens, so all the learnable tokens with the pair tokens. And at the end of this self-attention process, we only keep the learnable tokens. The graphics here is a bit misleading. The number of learnable token is much smaller than the number of paired feature tokens. The learnable tokens are 32 tokens, whereas the paired features are around 200 due to the Dino and clip features. But yeah, so each pair is encoded through this self-attention pooling and compressed in this shared smaller representation space. And as previously, we still want to avoid merging features for different pairs. So each pair is independently encoded through the pair fusion, again, to avoid any information leakage. And this encoding concludes the first phase of the of our LOTS pipeline. And now we need to inject the information inside the diffusion model for image conditioning, for generation conditioning. However, this comes with some challenges. In particular, due to the nature of the design process, we are left with a variable number of pair-centric features depending on the number of items that compose the outfits, which in turn makes traditional residual injection impossible due to the dimensionality mismatch between the features and the model features. As you may know, injecting through residuals requires the dimensionality of the features to match. And usually what people do is either concatenate in the channel dimension, for example, different conditioning. However, this would kind of require the model to have to expect a fixed number of conditioning, which goes against our will to have a variable number of pair-centric features. There is, however, another way that the community has found to solve this issue. And in general, when dealing with multiple or variable number of conditioning, one solution that the community found was to merge these features into a set of fused feature set through a single step merging operation, which is usually either a weighted sum or an averaging or mean pooling of some sort between these features. Once you have then fused the features, you can inject them into the diffusion model, since the features will have a fixed size, and these features are so used for conditioning. However, in our experiments, we found that the single-step merging operation is not effective and in fact degrades the conditioning information and contributes to attribute confusion. And here we have an example of the consequences of this single-step operation. So these two images have been generated with the same model, which is the pre-trained T2I adapter. However, the image on the left is generated by using a single sketch of the entire outfit, encoded and used as conditioning to generate the image on the left, while the image on the right, for the image on the right, we created embedding for each item in the sketch, and then fused those embeddings through weighted sum, and used those embeddings for conditioning. And you can see that apart from the attribute confusion, which is present in both images, we can see that the image on the right also displays some degradation in the sketch following, where you can see that the model is not posing as you would expect from the sketch, as instead posing a little bit different. And during our qualitative exploration, we found that this happened very, very often. So we wanted to take an alternative approach to information injection. And we do so by setting ourselves two goals. The first one is that we want to maintain the flexibility in the number of conditioning. I've stated already that this is important in the outfit design process. And now, given what we just found, we also want to avoid merging the features and thus reduce attribute confusion altogether. We do so with the process that we call the third fusion, which works as follows. First, we concatenate the pair-centric features in a single sequence of variable length, again, depending on the number of items that compose the outfits. Please note that despite the concatenation, there is still no interaction between the pairs. This is done purely for an engineering point of view, and there's no interaction between the pairs at any point in the process. Then what we do is we augment a pre-trained text-to-image diffusion model, in our case, Stable Diffusion XL, with additional cross-attention layers, as you can see at the bottom here. The use of cross-attention, or the attention mechanism in general, is crucial for our task, since thanks to the sequence-to-sequence nature of the attention mechanism, we're able to inject the concatenated pairs without any assumption on the sequence length, thus achieving the flexibility goal that we set ourselves. More importantly, this flexibility allows us to avoid merging the pairs in a single-step process, as we mentioned, as we saw previously, and we can instead defer their fusion throughout the entire denoising diffusion process. In particular, what happens is during inference, at each denoising step, the cross-attention layers can dynamically decide what information from which pair to inject inside of the model, creating so this implicit fusion or deferred fusion throughout each diffusion step process. Note that we are still able to use the global conditioning coming from the pre-trained text-to-image model, as you can see on the top. And in our experiment, we use a generic description, such as a photo of a model posing, just to give the overall structure of the image. We will talk a bit more about this towards the end of the presentation, so keep in mind the presence of this general description. So this concludes the overall pipeline, and together with the general description and the localized pair conditioning, we're able to generate the final image with the attributes correctly localized, such as the plain blazer, the striped pants, and the floral shirt. To train and evaluate our methodology, we also present a new dataset called the Sketchy dataset. And Sketchy is the first fashion dataset with multiple localized sketch text pairs for each image. Sketchy is built on top of the popular Fashionpedia dataset, which was published at ECCV 2020. And Fashionpedia presents images of outfits worn in different contexts, and each image is annotated with the segmentation mask of the items that appear, which are paired with the textual attributes that describe the properties of these items. We augment this data first by generating a localized description of the item using the ground truth attributes of Fashionpedia and a pre-trained large language model to sort of simulate the natural language that the designer might use during the process. And then we generate also the localized sketch of the item with a pre-trained image to sketch model. And we pair it to the description, creating this localized sketch text pair. When multiple items are present in the image, such as in this case, we repeat the process for each item, and we achieve the multiple localized sketch text pairs. In total, we achieve around 46,000 images divided between training and testing, with between 1 and 6 localized items per image, with an average of 2 items per image. The dataset has been published, is available at the project page that you can see on the top left. So we then evaluate both zero-shot and fine-tuned approaches on Sketchy and compare them to our LOTS methodology. And here, what you can see is we have 2 types of metrics. On the left, we have more global alignment metrics, which are image-level metrics, for example, FID for image quality and global clip for text guidance. Whereas on the right, we have compositional alignment methodology metrics, such as local clip and VQA score for localized text attributes evaluation, and SSIM for sketch guidance. What we found in our experiments is that some methodologies are biased towards sketch guidance, such as the multi-T2I adapter here achieving an high SSIM, but a low FID and VQA score, for instance. Other methodologies are biased towards text guidance. For example, T2I adapter achieves a nice attribute localization with a nice VQA score, but a low sketch guidance with a low SSIM. In contrast, LOTS strikes a balance between all the guidance and is able to achieve the best overall result across metrics. More comparison and qualitatives are also available on the paper, so if you're interested, you can find out more in there. Speaking of qualitatives, here we have some qualitative results. And you can see that even with a little amount of items, such as on the bottom here, with 2 items, you can see that other methodologies already struggle to correctly localize, for example, the dots in the crew neck at top, which is not appearing in any item. And on the top, I think it's another great example of the single-step merging problems of the conditioning in the multi-T2I adapter, where you can see that despite providing clearly a sketch of a single person, multiple people appear in the image, again with, of course, attribute confusion throughout the image. And this is an example of how complicated the description can become in the Sketchy dataset. You can see that the attributes are not limited to just pattern attributes. We also have attributes that describe, for example, the neckline type, the sleeve length, the fit of the outfit. So this description can become quite lengthy and complicated. However, LOTS is still able to use this complex information to correctly generate the image. We also wanted to evaluate the impact of LOTS on attribute confusion, and we do so with a specialized user study. In this user study, we ask the reviewers 2 types of questions. And the first one is an attribute recall question, which probes for attributes appearing in the correct item. If you recall the original example, we requested a plain blazer, some striped pants, and a floral shirt. So an example of attribute recall question might be, are the pants striped? And in this case, we can see that both images are correct since stripes appear in both images, in the pants on both images. The other kind of question you might imagine is an attribute precision question, which actually asks for probes for attributes appearing in unrelated or wrong items. Again, since the stripes were only supposed to appear in the pants, as you can see in the example here in orange, an example of a precision question might be, is the blazer striped or is the shirt striped? And in this case, we can see that while the image on the left is correct, there are no stripes in the blazer, the image on the right is wrong because it displays some attribute leakage where the stripes are appearing in the blazer despite only being asked in the pants. With these types of questions, we then compute precision, recall, and F1 scores and see that LOTS outperforms all prior methodologies also in attribute confusion, or rather reduces attribute confusion the most. Of course, we also conduct some ablation studies. You can see here in the table. And what I wanted to highlight is that first, we also try different encoders for the sketches. And sketches are a bit tricky because of the sparsity of the information that we already saw before. For instance, we tried training an encoder from scratch or using clip and bleep too. But what we ended up finding out is that Dino v2 in our experiments was the best image encoder. And we believe it is because of the fine-grained nature of the Dino v2 features because of the way it is trained. And so we ended up using Dino v2 as a sketch encoder. Another example that kind of supports our findings is this highlighted in orange, the mean pooling, where instead of using the third fusion, we do the single step operation that we mentioned before, and we fuse the embeddings coming from different pairs using an average or a mean pooling. And in this case, we can see that the third fusion, so the approach used by LOTS, improves attribute localization by around 7 percentage points. So comparing the orange part here with the bold here on the bottom. Finally, we also tested with the we also did some experiments with the sparsity of sketches. And you can see that by using the pair-former, we're able to improve the sketch guidance by around 6% when compared, for example, to the no pooling methodology, no pooling ablation study, where we basically did no compression at all for the sketches and kept all the tokens coming from the sketch. And you can see that this achieves the second lowest sketch guidance because, again, the features are very sparse and the model would just ignore them during training. So there are some, during our experiments, of course, and we also find some interesting future directions. The simpler one would be to just extend this work to newer models. By now, this work is almost 1 year old. So, of course, newer, stronger models came out. For example, the new diffusion transformers, the most popular ones that you can think about. And we believe that our approach can be easily extended to this diffusion transformer case because it's a simple matter of concatenating the pair features. And another interesting direction is to extend the conditioning to other localized conditions. The simplest one might be segmentation masks, since they're already present, for instance, in Sketchy. But another interesting input that I received, or feedback that I received when presenting this work, was, for example, conditioning on the fabric that can be, or textures of the items that can be created. And again, I believe this is a very interesting application for the fashion domain in particular. And speaking of fashion domain specific improvements, another interesting thing might be to allow for support for different styles and abstraction levels of both sketches and language. The sketch part is pretty intuitive, I believe. Every person draws it with a slightly different style, so it might be, it for sure is needed to expand these methodologies to support different styles of sketches. But what we also found is that the fashion experts also use a different language when describing the items. And they use what we call a abstract language, as you can see here in red, which contains some abstract adjectives which cannot be easily grounded through vision, and which is in contrast with the concrete language that is commonly found in large pre-training dataset with which these vision language models are trained. And we found that this creates a gap in the performance of these models. And we believe that bridging this gap is also essential to provide useful tools for the fashion industry. The last direction that I want to talk about is the use of the general description that I mentioned earlier. You might have noticed that the general description that we chose contained no information regarding the outfit, any information regarding the outfit. And this was a deliberate choice because in our vision, we want the general description to be sort of a conditioning on an image level. So we want to be able to provide this top-down and bottom-up conditioning where the localized pair features are used to generate, the outfit itself, whereas the general description is used to kind of change, for example, the background or the style or the overall look of the image. And here we have some preliminary results, which is something that kind of inspires us to continue investigating this direction. And all these three images are generated using the same localized conditioning. And the only thing that we change is the general description. And you can see that, for instance, on the left, we used a model at the wedding, whereas on the right, we asked for a goth model. And you can see that the goth model has sort of paler skin with dark makeup around the eye, which is in line with the goth style. And we believe this, again, is a very interesting future direction for allowing a more general use case for our methodology. Finally, we are releasing a platform where you can test both LOS and your designer skills. And this platform, as I teased a bit before, you can draw as many items as you want to compose your outfit. And then this information is fed to our LOTS adapter to generate the final image, which should give you a nice preview of what your outfit might look like. And this about concludes my presentation. So thank you so much for your attention and to the organizers for having me. And I'm happy to answer any questions both here and offline. So feel free to reach out if you'd like. Thank you so much again.